Hey everybody, what's up? My name's Florian. Today I'm going to show you how to create an XPresso setup that lets you shoot objects onto targets. Looks like this. You can use this, for example, if you want to make a basketball hit the hoop, or if you have a mortar that needs to hit a target, or arrows shooting at something. So we're using Cinema 4D's dynamics here. The sphere is a rigid body object, and the initial linear velocity is what's actually driving the animation. So these values here are shooting the sphere into the air, so it will always hit the target, unless of course the velocity is too small and it cannot reach the target. We can set a velocity on our target object, so on our null here. We can set the velocity higher or lower. If we set it, for example, to 1,000, it will, of course, start off in a much steeper angle to hit the target. Or if we go down to 300, it will not even reach the target because it's too low. So we're using XPresso to calculate this stuff, and also a little bit of Python. And I will try to explain best as I can, but I'm not really a Python pro, so bear with me if I have a little bit of a hard time to get my head around some of this stuff myself. So before we even start, I want to go through the theory behind this thing. If we're calculating trajectory angles, so as you see here in this great web application, this guy Maciek built, you can see that if you have a starting point 0 and you want to hit a target at a point x, y in space, there are actually two angles that you can shoot from to hit the target. So it's this higher angle here and the lower angle, and eventually this thing here will say projectile cannot reach target with velocity of whatever your velocity here is. So we can only hit our target if we have a certain velocity that is capable of actually shooting the projectile, or the sphere in our case, to hit the target. And the underlying formula is this one. So it's theta, which is theta, which is the angle that we're shooting at, is this formula here. And I assume you know basic trigonometrical formulas and math. So arctangent is just a function that calculates something. So as I said, I'm not really good at this stuff myself, but if I type it into the Python editor or XPresso, it works. So what we're having here, we're having some variables. V is our initial velocity, so this is the one that we're setting here in our target object. This is this guy. And what else do we have? G, which is our gravity. This is our Cinema 4D project's gravity. X, in that case, is the distance on the x-axis from our 0 point, and then we have y, which is the distance in y from our 0 point. So knowing that we have so this is our formula, and here we have a square root in our formula. Actually, I will post a link to this site in the descriptions, and I will also post a link to the C4D files, of course. So knowing that we're having a square root here in our equation, this means a square root only works if whatever is inside the square root is greater than or equal to 0. So we can assume that this square root is what's basically more or less checking if our velocity is high enough. So if our velocity is too low to reach our target, and in here we're getting this error message here, then this means that in our equation, this guy here, this whole piece of the formula is lower than 0. So this is what we know, that if this is lower than 0, then we cannot hit our target, which will help in our C4D file as well. So let's go back to Cinema, and In here in our XPresso script, I'm also checking if we are actually able to hit the target. So I'm checking if this, he calls it somewhere here, the delta value. So the delta is whatever is inside here. If this is greater or equal to 0, our target icon is going to be a star. So this means we can hit our target. And if I go farther away with our target, you see it turns into a sphere. So we are not able to hit our target if I press play. See, we're shooting not far enough. So, all right, let's check out our actual XPresso script. This is what it looks like here. We'll build this from scratch, but just so that you have a little bit of an overview here. We're calculating distances and putting it into our Python script that we are about to write, and we're outputting it again and feeding it into our dynamics body tag, which is on our sphere. The second part of the tutorial is, hold a second, if I open this guy up, where is it? This one is when we have multiple objects and all of them are driven by one XPresso script and all of them are hitting the target no matter where the target is, of course. So we're not only calculating this for one object, we're calculating it for a whole hierarchy of objects. And for that, we need to write a second Python script to help us with our iteration through all the separate objects. So, but I will go to that later on. So let's just start with our single mortar or basketball or whatever. So all right, let's make a new project and start the whole thing from scratch. We create a sphere, which is our bullet or basketball or whatever. Give it some random radius, and I'm making a target null. Call it target. And for now, let's just turn on the grid for a second here. For now, let's just work on the X and Y plane, just so it's easier for me to describe what I'm doing and for you to understand maybe. So let's just go to front mode here. So our sphere is on 0, 0, 0 position, and our target is on, let's put it to a round number, 300 in X. So we have to calculate the angle that this sphere needs to shoot at a certain velocity to hit our target on this X position. So let's just make ourselves an XPresso tag on our target and maybe close this for a second. Let's also add some user data. What do we need? We need to set a velocity, and this should be a float slider, and the unit is meter. And let's just leave this stuff set to the default values here. And as I showed you earlier, there are actually two angles to hit the target. So let's just make a switch to switch between those two angles. Let's call this high angle, and this is a bool and default on. So now we have a fancy switch here. Let's set our velocity to, I don't know, something. So let's go to our XPresso and let's find a way here to make this big enough so you can see what we're doing. All right. So the first thing we need to do is, I would say, transcribe our formula into the Python scripting language so we can work our way around it. Let's just make a new node, Python. So this is our Python node here. It has two inputs and an output by default, and the default calculation is just adding those two input values. We can just delete this, and let's rename our inputs here. So what do we need? If we go back to the formula, we have 4 variables actually. It's the velocity, the gravity, our distance in x, our distance in y. Yeah, that's 4 already. So rename this one distance x, and this one distance y. And then add another input by clicking here on the blue corner here, and it should be a float value, and rename this to v, which is our velocity, and get another float and rename this one to g, which is our gravity. By command double clicking on the title bar here, it will automatically resize the node so all the inputs and outputs are visible. Then let us rename our output to angle, and all right, so what we want to do, if we have a simulation rigid body tag on our object and we turn on the custom initial velocity here, we cannot enter an angle that at which we are shooting our object at, so we can just enter velocities in x, y, and z. So we have to actually calculate separate velocities for those 3 values. We cannot really use this angle here. So we're actually outputting the angle, but we're not really using it for our dynamics body tag. So we're actually making a new float value, which we will call x, and a new one which we'll call y, and maybe also a new one which is just a bool, which we call hit. So this is just outputting 1 or 0 depending on if we can actually hit our target with the velocity that we typed in here. So, oh yeah, we also got our hit bool switch here. So we also need another, this could be a bool as well, input, and rename this to hit. Oh no, sorry, high angle. Okay. And again, command double click to resize the Python node. So let's start our Python scripting. One thing I noticed is whatever your script is doing here, be sure that you don't have extra lines at the end of the script. Otherwise, the Python node will not work properly. So always be sure to delete whatever is below your actual Python script. We will start off by calculating our this thing here. We call it delta, because we need this to check if we can actually hit the target. So let's just keep this in mind here. Maybe I'm able to resize this stuff like this. Perfect. Okay, so let's just quickly calculate this. Oh yeah, in Python, whatever output you have set here, you will also have to declare it as global variables here. So we have to say x and y and hit. So this makes the Python script output stuff outside the script and not just calculate it inside the script. Let's make this a little bit bigger here and get rid of this one. And all right. So let's calculate this delta value here. As I said, it's just this this bunch of code here. Delta equals pow is the power function, which means we can enter v comma 2. So this means it's v to the power of 2. It would be the same as calculating v times v, but it's just nicer to do it with this function. v, oh yeah, times 2. Wait, is this the right equation? Yeah. Sorry, yeah, v to the power of 4, all right. I was looking at this and not at this. Minus, and open brackets, g times, and I'm just looking at my second screen here, so I don't need to calculate the brackets that I actually need to open and close all the time. So g times the x power of 2, close bracket again, plus 2 times dy times power. Oops. It's a little bit annoying that Cinema is automatically opening and closing brackets for you in Python. I think this should work. Let me just double check. Opening. Yeah, all right. So I think this should work. This is this part of the equation now. We can check what this guy is outputting here. So we will just temporarily say this is x, and we can turn on our result here. Where is it? Here. This will of course output 0 now because we do not have any values for this. So let's just manually type in we know our distance in x here, so this should be 300, and our velocity is, let's say, 200, and our g-force is 1000. So we're getting a negative value here, which means our equation in general is not solvable, which means we cannot hit the target. So if we up the velocity in our theoretical construct here to 1000, all right, with 1000 we would be able to hit our target. So our value here is a positive value, and it seems to work. All right, so let's just work with it for now, and we will see later on if everything's working correctly. So if our delta value is positive, we can commence with our formula here. So let's just type this: if delta is greater than 0, we're calculating our angle now. So this is ANG equals, and now this is the actual formula here. So what we need to do, we need to calculate an arctangent, which is in the math library, so math A10. And to use the math library, we will also have to import the math library up here. So let's just type this thing up here, math A10, and then I'm looking at my second screen again to write down this formula, so I'm not doing any errors here. So this is v to the power of 2, and then you see this equation actually has two solutions. Those are the two angles that we can calculate. It's one time is the plus and once it's the minus. Now we're calculating the angle that results of our plus equation. So plus math square root of delta, which is the thing that we just calculated up here, and close bracket again, and we're dividing this whole thing by g times our x distance, and close a couple of brackets. All right. So this is happening if our delta value is greater than 0, so we can actually hit our target. If our value is smaller than 0, so if delta smaller than 0, then we will just set our angle to 45 degrees. So we're still shooting into the direction of the target, but we know that we won't reach it, but we'll still try to shoot at 45 degrees, which will naturally give us the best distance. So let's just quickly Google the radian value for 45 degrees. 45 degrees in radian. Okay, 0 point something. Oops. Okay, great. So now we actually have calculated our angle that we need for our sphere to reach the target. We can make C4D bigger now again because we typed in our equation already. So we can not use our angle per se with the dynamics tag, so we need to calculate x and y values for this. But this is very simple. This is just x is the cosine of our angle, and y is the sine. Oops, that sine of our angle. So whatever our angle is, our cosine is the x part of this angle, and our sine is the y part of the angle. So we will get a value between 0 and 1 for x and y, and just by multiplying it with the velocity later on, we will result in our correct initial speeds. So there's one more thing that we need to add in here. So if we can hit our target, so delta is greater than 0, we also have to decide which angle we should use, our higher angle or our lower angle. So if high angle equals 1, we will calculate this equation, and let's just copy the whole thing. And if our high angle is 0, we will just change the equation to the one with the minus sign here. And we also want to output our hit variable here with the 1 or 0 depending on our delta value. So hit is 1 here, and hit is 0 if delta is smaller than 0. So alright, that looks good. I think our equation will work now. Let me just double check again with my second screen. I think I have all the brackets in the right place. If we go to our if we click Open Python Editor and click on Execute, we have no errors. That seems to be alright, so there's no syntax errors or anything. So let's plug in some stuff into our node to check if it's actually working. First of all, let's make some result nodes on our output ports. Of course, we're getting results now because we have manually set input values here, but those will be overwritten later on if we connect stuff into the actual ports. All right. So let's do this one by one. So our dx, our distance in x from our sphere to our target. To calculate this, we need both of those objects here. And we need both global positions. And again, by command double-clicking the nodes, they will scale up. So all of the ports are visible. What do we need to calculate our x distance? We will need our we could use our just the position X, but we know that we also need our position Z later on because we're moving our target in Z space as well. So we will go for the global position, and we will use the vector to real node and the real to vector node, and plug this one in here and connect X to X and Z to Z, and do the same thing for our target object. So what we've done now, we basically got rid of our Y distance by not plugging it into the reals to vector node, so this stays at 0. So we're with those guys here. Let's just make it nice and tidy a bit like this. We can get a distance node, and let's make some more space here. You can get a distance node and calculate distance between those guys here. So this is our distance X value here. All right. And let's put this here. Okay. So our distance in Y is easily calculated just with a math node because we only have one value here. We need to subtract our sphere position. If we subtract the sphere position from our target position, and we make a quick result node. So see, now we have 0 distance between those guys in Y because they're on the same Y level. But if I raise my target, we see we're getting a negative Y value because we're subtracting this value here from 0, which is exactly the opposite of what we want. We need it to be a positive value, so we can just switch our inputs here and get a positive value for the node now if we're higher in Y, and a negative value if we're lower in Y. All right, let's just turn on the animation refresh. All right, so we got an instant refresh on our result nodes here as well. Okay, so we can plug this guy into our dy port and just delete the result node again. Put this over here. Okay, so our velocity input is actually just our user data velocity here, connected to that guy, and our high angle input port is just our high angle output here. All right. So all we need now is our scene gravity. So let's just press Control or Command D and go to Dynamics. And this is this value here. So we could just enter it manually in here, but if you decide to change the scene gravity, you would have to change it here as well. So let's just take this guy here. You can drag this project icon down here into the XPresso editor, and you have access to some of the stuff that's going on here. So if you for some reason need the frames per second of the project, or the where is it, the file path, for example, to set up a script to make render settings depending on your file name, you can do it with this node here. Unfortunately, you do not really have access to the dynamics here with just dragging in the project icon. So what we need to do is delete the object here and go back to our dynamics and make a quick set driver, set driven. We get a new expression here. Just double click and copy our dynamics node from this XPresso script to this script. So we have it here, and just plug it into the Python node as well. All right, so let's just get rid of this expression again here. Okay, so now everything's connected and we have some values going on here. It's time to check if our stuff works. Ah, yeah. See, if we're getting closer to our sphere, the values are changing. So yeah, exactly. So if we're getting farther away and we're not actually able to hit our target, so our hit value here is 0. Our angle is going to be 45 degrees, which is this value here, and those is the X and Y values that we get. So see, if hit is set to 1, we're actually getting our angles calculated properly. All right, so let's just check this out. If now we have an angle of 0, a hit value of 0, because we're not able to hit the target. But if we up our velocity, yeah, see, now our values are changing, our formula is working. Great, so let's just use those values now to calculate our actual velocity that we need to reach our target. This is a very easy calculation, so we can just drag our dynamics body tag into XPresso here, and it's under dynamics, initial angular velocity, no, linear velocity. All right, so we need to feed in x, y, and z values for here, for this tag here, and what we need is we just need to multiply those values with our velocity. So we'll get a another math, oh, was already there, another math node, set it to multiply and duplicate it, and drag our velocity in here and in here, and or maybe let's drag it to the bottom port and get our y value in here and our x value in here, and to feeding it into this input, which is a vector input, we need another real to vector node, x and y, and in here. So if we start our simulation, works perfectly. Great. So this is working, and let's make our scene a bit shorter, and let's see if our high angle button works as well. Yep. So this is the high angle and this is the low angle. Perfect. And let's change the velocity. Great. Okay, this is working nicely. So there's one thing that we need to change though. This is working on our XY plane now, but we want to actually have it to work on all 3 dimensions. So to do that, we will just add a target tag onto our sphere. So our sphere is always disable pitch. Our sphere is always facing our target object. The thing is, it's facing it with its z axis, our blue axis. You see, if I zoom in here, if I move around my target, the sphere's z axis is actually facing the target. So we always need to shoot along our z axis, not our x axis. So we just need to change this output here to this one instead of this one, and maybe let this target be a bit more visible by being a circle, and also introduce a floor to the scene. Cool. And maybe a tracer to the sphere so we can just really see our flight path. Oops, this was not a tracer. This guy. And set it to this. All right. So this seems to work perfectly. Great. Deactivate our grid. Okay, so this is working. Now we want to adapt the whole thing to work with more than one object. So Let's just quickly put this guy into a cloner here and set it maybe to grid 1 and collapse it again. So the thing is, with dynamic objects, we cannot leave it in a cloner object because we need to access all of the initial velocities separately, which is not possible as far as I know when it's inside a cloner object. So we need to resolve our cloner into a null and get rid of all those targets for now, and just put it into a fracture object instead and get rid of our cloner null again. So we're using this fracture node now to hold our spheres, and we're using a fracture and not a normal null because we can now use MoGraph effectors on our fracture node to actually place the spheres exactly like we would have done with a cloner. So let's just make a quick matrix here, for example, and set it to radial, count 9, plane XC, and make it like this. And our fracture node will get an inheritance effector and set this to animation, and it will inherit the matrix object, or will it? Wait, maybe it's direct. Oh no, this button needs to be pressed. Morph motion object. So now our spheres are getting their positions from this matrix object. So if I change the matrix object size or something, our spheres will change their positions accordingly. And just for fun, let's put maybe a random effector on top of that, and maybe just 20 in Z, and so they're not really evenly distributed here. Okay, and on top of that, we will add our target effector again. So this will affect all our fractures now and let them target our, oops, before you do this, before I do this, deactivate the use pitch. So we'll drag our target object into the target object slot in here. Now all our spheres will target the target correctly. Great. And let's go back to our XPresso. And there's a couple of things that we need to change here. So we don't have an object here anymore because we have now a fracture object instead of our sphere. So let's get rid of this one. And we need to access every single object inside the fracture here, which we will do with the data node. And we'll get the object from here, put it in here, and we will also need an iterator, iteration. Let's put this one here for a second. We need this count to be subtracted with 1, and this goes into the iteration end. Alright, and we need another data node. This will also be this guy here. We will use the position, which is the global position of each of the spheres here. This goes into our vector to real here. and we iterate through all the indexes of this data node. We need to use two data nodes because we cannot use discount for the same input here, because then we would have a loop, and XPresso doesn't allow us to do a loop inside a script. So now we're calculating each of the positions, and like with the iteration node calculates each single position, runs it through the Python script, and outputs it here. But then we will also need to tell it to actually output it to each individual dynamics body tag up here. So we will going to use a tag object here, plug it in here into drag this one here for a second and get rid of that one because that lost its linkage. All right. So connect this to the tag, and now all we need is an input for our tag node here. The problem is we would need to access the hierarchy now and access each specific object depending on the iteration or where our iterator is at this point in time. So if we use the hierarchy node here and connected this object to the hierarchy node and outputted this object in here, this doesn't work because this guy is a loop and this here is a separate loop. So we need to find a solution to use this iterator to actually generate the same loop, or to use this loop here to get an individual object out of our hierarchy, which our hierarchy node, as far as I know, will not allow. So we'll just really quickly create another Python script to do the job for us. So just type in Python here and we can get rid of this output. No, actually, let's just rename this port. So this is an index here, and no, this should be a count. So what we're going to do, we're going to create a Python node that actually allows us to access only one individual object in our hierarchy, in our list of objects inside the fracture object. So what we also need is a link, and we call this guy object. And let's get rid of one of those here, delete port, and get another link here and call this hierarchy, and this will be our index. So in our Python node, let's get rid of this calculation here. So inside our Python node now, we will define a new function. Let's call this get object by index, and we need a start object and we need an index. So what this function will do, we start with our result and declare it as start object dot get down. So this will just basically the same as in a hierarchy node. If I quickly create one here, this works the same way. Your start path is down and your iteration path is next. So we're just going to kind of recreate this in Python here. So our start path, which is our the object that we're going to put in here is our start object dot get down, which is the command for in Python to get down one object or one level in the object manager. So, all right, and then we will generate a quick loop for I in range of 0 to index. This means if whatever our index is, it will add more commands at the end of our start object variable here. So this will be result, which is already start object.get down, and will add behind it or at the end of it will add the variable get next. So it will add get next as many times as our index variable specifies. All right. If our result is none, no, actually we don't need this because our result will never be none. Okay, and then we're going to return our result. So now we created our own little function that just adds more get next commands after the result string each time the loop goes through the this range here from 0 to index. All right, so and inside our main function, we will also need another output, which is object, and our count will be the length of our hierarchy object. So this is hierarchy, this shouldn't be a comma, point get children. So the count will output the amount of our children in our hierarchy, same as this count value in the hierarchy node would do. All right, and our actual calculation will be if index is smaller than count, object equals get object by index hierarchy index, and if not, oops, else object get object by index hierarchy 0. So what this does, if our index, so whatever we specify in this input here, is lower than our count, so if this index number here makes sense more or less, so if we have, for example, 10 spheres in our fracture object and we want to have access to index number 50, this wouldn't work because we don't have a 50th object to reference to. So we will just calculate or output the object with the index 0. So this is just for the purpose of that we're not getting any error messages. Okay, let's open this thing in the editor and execute, and we see we're getting an error message. So what's the problem here? Oh, all right, this should solve it. Execute. Here we need another thing. Okay, now it works. So we can get rid of this hierarchy node, and this Python node here now takes this iteration to just output one object, and this is the object that we will throw into our tag node here. And I think this should work now. Looks like it. All of the balls are jumping into the right direction, and they're also jumping with the right speed, the right angle value. So they're all trying to hit our target. Great. And just for the sake of this tutorial, that those guys are not all triggered at the same time, we will create a quick ghost collider object to trigger the dynamics on those spheres, ghost body, and maybe make it like this, rotate it a bit, go to frame 0, and keyframe our rotation on frame 0, and on frame 20 we want it to be rotated by 180 degrees. Keyframe it again and set our dynamic tags to trigger on collision. So now the dynamics will only start when those spheres got hit by the ghost collider object. So I can make this invisible. All right, perfect. Okay, I hope you more or less understood what the concept behind this thing is, and if you have any questions or any feedback, or if you even know how to not use your own Python node and do this thing with the hierarchy node or something, let me know, because I'm not aware of a way to do it without building your own Python node for that. So I will post a link to this scene in the comments and or in the video description, and yeah, have fun with it, and see you soon.